So in this video, we're going to be diving into the heart of logistic regression. But before we get there, we need to see a few like conceptual and mathematical framework objects to kind of set the stage for what's going on. So to get our feet under us, we're going to be dealing with an example related to spam filter. So this is a very super applicable example in the sense that, and this is a funny story, phishing attacks and other forms of spam that are meant to draw you in often intentionally introduce spelling and grammar issues into their emails, and it's a really interesting like little psychology and actually data science thing of like why these spammers and scammers do this. But it is a well-known tactic, and we can talk more about it offline. It's a little bit too long of a diversion for a video like this, but suffice to say that looking at how the number of spelling errors in a message is related to the probability that, or the whether the message is spam or not, is an interesting and timely one. So in this particular data set, for instance, here we have an email message that has 91 spelling errors, and it was spam, 7 spelling errors, it wasn't spam, 85, it was spam, and so on and so on. So a first step at getting our feet under us here would be to just display the data. So here I've plotted whether the message was not or was a spam message as a function of the number of spelling errors that it contained. And we see a couple interesting features here. So for instance, if the message does not contain any spelling errors, it is definitely not spam in this data set. There are no kind of spam messages with a small number of spelling mistakes. If there's an overwhelming number of spelling mistakes, then it is for sure spam in this data set. And then in the middle, we have this mixed kind of message. If we have 50 spelling errors, it could be either way. It could go, it could be a spam message or not. And one of the bad parts about displaying the data like this is it's not quite clear whether, for instance, at 50 spelling errors, whether it's more likely or not that the thing is going to be a spam message. So we're just going to change the view a little bit. So what I've done here is bend the messages. So for instance, from 0 to 5 spelling errors, from 5 to 10, from 10 to 15, 15 to 20, and so on and so on. And then for all the messages within each bin, I've calculated the probability that a message in each bin is spam. So for instance, we see the kind of the same thing. If a message has between 0 and 5 spelling errors, there's a 0% chance that a message in that group is spam. Whereas if we go, for instance, from like 50 to 55, like this data point here, if you have between 50 and 55 spelling errors, there's like a 70% chance that you're spam, and so on and so on. So if we were to model the situation now with a linear model, we would not do well. So one option would be to try to fit this transitional region in the middle. This is pretty linear, that's pretty good, but we completely miss these edges. You know what I mean? Like we're not capturing the behavior when we kind of saturate spelling errors here or saturate the lack of spelling errors here. We get the middle well, but the ends poorly. One of the other things I don't like about this from a mathematical point of view is that if we extended this line further, there are spelling errors where this model would predict probabilities greater than 1 and probabilities less than 0 on the other end. And mathematically, this is not super nice. It's not super friendly or well behaved, we would say. So the way to get rid of that would be like tack down the ends and basically say, okay, well, I'm just going to basically say that I'll never go above 1. I'll make the maximum number of spelling errors I ever see probability 1, and I will make the minimum number of spelling errors I've ever seen probability 0, and I'll just draw a line connecting those two. And sure, you get those 2 data points right, but you screw up everything else. Like you miss all of the interesting trends in this data by drawing a line in this way. And so what this is saying is, while linear regression might ultimately be a good way of thinking about this, right now it isn't. Like we can't just port over linear regression directly to this way of thinking about the data set in hope of having any success. So let's play around with the edges and see if we can't do something a little bit more interesting. And to do that, we're going to be introducing the concept of odds. So, funny story as an aside. So odds are used in betting a lot, as you can imagine. It's all about probabilities and how likely various situations are. And so when I came to Babson and started teaching in the undergraduate program, I was teaching a lesson on odds and probability. Students were getting it really fast. And I was like, oh, I'm such a good teacher. Look at me. I'm imparting knowledge to young minds. And one of the students later told me, it's like, oh no, it's because we bet a lot. I was both horrified and impressed that students were already deeply familiar with odds, but that is a short aside, I guess. The odds mathematically are the probability that an event occurs, that we call that P, divided by the probability that it doesn't occur. That's 1 minus P. And so, for instance, if we have a 50-50 event, like a fair coin toss, for instance, the odds are 0.5 divided by 1 minus 0.5, which is also 0.5, or just 1. And in kind of betting circles, we would say the odds are 1 to 1. For every one case that where the event happens, there is one case where the event doesn't. For every one case that we get heads on our coin flip, there's one case where we get tails. Obviously, it doesn't have to be a fair coin flip. And if we change it to something like 0.2, there's a 20% chance the event happens. Everything works in exactly the same way. We have 0.2 over 1 minus 0.2, or 0.8, and that gives us odds of 1/4. Another way of saying that is 1 to 4 odds. For every one event where the event occurs, for every one time the event occurs, there are 4 times when the event doesn't occur. And similarly, if we flipped it around to 0.8, there's 0.8 over 1 minus 0.8, or 0.8 over 0.2 gives us 4 to 1 odds. So the big idea here is that a probability is always between 0 and 1, but odds are always between 0 and infinity. So we've transformed the range in an interesting way. You can have 1 to 1 billion odds. That's an odds very close to 0. Or you could have 1 billion to 1 odds, and that is very large. And so that number can get as large as we want. And in the other case, the number can go towards 0. And so we've kind of transformed the range from 0 to 1 for probability to 0 to infinity for odds. The good news is the higher the probability, the higher the odds. We call this a monotonic relationship. As probability increases, the odds increase always. And that's really convenient mathematically. So the question is, why do we care about odds? Like, what are we going to do with odds? Like, why have we spent time learning about this? Well, let's go back to our probability plot here. And instead of looking at the probability, I'm actually just going to plot the odds. Another way of saying that is for each one of these points, I'm just going to take the points value, like 0.78, divided by 1 minus 0.78 to turn it into the odds. When I do that, I get a graph that looks like this. I'm sorry, I should mention this blue curve is just me fitting a curve to the data that we had, just so you can kind of see what it would look like if we had more data. I don't want to give the impression that data will always be that clean, so I want to show the scatter, but I also want to show kind of the overall trend and how it gets transformed. So if we transform both the trend and the data, we get a figure that looks like this. This kind of nothing happening for a while and then this huge upsurge is the characteristic shape of an exponential function. This kind of, sometimes it's called a hockey stick graph, which is very North American centric. I guess not only North American, it's Northern Hemisphere centric. I don't know. But anyway, not that many people play hockey. But it's like nothing's happening and then all of a sudden it shoots up like this. This is classic exponential behavior. The good news is we know a lot about exponentials. Whereas that curvy thing may have looked strange, this exponential, once we start seeing this, we're home. This is familiar mathematical territory. And in particular, we know how to undo exponentials. If we take the logarithm of an exponential, we undo that operation. So here's what I propose. We don't look at the yes-no of whether it's a spam message or not. We don't look at the probability of this being a spam message. We don't look at the odds of it being a spam message. We look at the log of the odds of it being a spam message and see what we get. If we do that, so I have a confession. I mean, I made these data synthetically. I made these data, and every time I just looked at the figure. I was like, wow, that's like a really good fit. Like, look at that line. It's so amazing. Even when you generate the data yourself, it's still amazing that it pops out this strongly. So if we plot the log of the odds as a function of the spelling errors, we get a virtually linear result. Even though that original data set looks so sloppy, right? It looks so sloppy. And then we have this curve, and then that's strange, and this exponential. But if we just look at the log of the odds, that thing is very linear in a lot of situations. And this is the signature that logistic regression is designed to detect. So when we say a logistic regression, this is exactly what we mean. We mean that the log of the odds that a message is spam is just a linear function, beta naught plus beta 1 times s. S here is the number of spelling errors. So it's just a linear function, plain linear function. But it's not the right-hand side that's interesting. That's just linear. It's the left-hand side of the function that's interesting. This is not just our target. This is a transformed version of our target, like seriously transformed, right? From categorical yes-no to probability, to odds, to log of odds. Like we've gone through a process here. But now that we're here, we can introduce all of the same stuff that we would normally do. For instance, we can say that if beta 1 is positive, this coefficient, then as S increase, the log of the odds increases, therefore the odds increase, therefore the probability increases, because all of those things trend up monotonically together. If the log increases, the odds increase. If the odds increase, the probability increases. So if beta 1 is positive, then odds go up as S goes up. Similarly, if beta 1 is negative, then as S goes up, the odds go down. And if beta 1 equals 0, then changing S has no effect on the odds. This is exactly identical in spirit to normal linear regression, which is awesome, right? Like in spirit, this is exactly the same. Now, it turns out that in the details, it's a little bit different. So let's dive into that. This is a math-dense slide coming up, so just take a deep breath, calm your spirit, and we'll just jump right in. So what we're assuming here is that the log of the odds is a linear function. So imagine I had two messages. One of them, message 1, with S spelling errors, and the second one, message 2, with S plus 1 spelling errors. What's the relationship between the odds that those two things are spam? Okay. Well, the first thing I've done is I've exponentiated both sides. So I have odds 1 equals e to this thing, and then I have odds 2 is e to this thing, except with s plus 1. I've just taken the exponential of both sides. That cancels with the log, and I have e to the beta 1 plus beta 1s, or s plus 1, as the case may be. So normally in linear regression, we would subtract these two things and look at the difference between y2 and y1. Here in logistic regression land, the thing that actually makes more sense is to take the ratio of the two things. So if I divide odds 2 by odds 1, notice what happens. You may have to review your rules of exponents and fractions and all of this, but essentially the beta naughts cancel, the beta 1 s's cancel, and we are left with just e to the beta 1. And what this is saying, if we rearrange it, is that odds 2 is just e to the beta 1 times odds 1. Another way of saying this is if we increase s by 1, like one more spelling error, then the odds that the message is spam increase by a multiplicative factor of e to the beta 1. My experience as an educator, having done this for a long time, is that that sentence still doesn't make sense. That sentence still doesn't click. So let's do an example with real numbers. So imagine we find the following linear regression model for a spam, for this spam example. So it's saying that the log of the probability that the message is spam, and it should be the log of the odds, rather, that the message is spam, is 0.1 times s. So what this is saying is for every additional spelling error in the message, the odds that the message is spam increase by a multiplicative factor of e to the 0.1. If we were to do that out, e is just a number. So if we were to take that number and raise it to the 0.1 power, we get something like 1.11. So what this is saying is that for every additional spelling error in the message, the odds that the message is spam are 111% of their previous value. So if I go from 10 to 11 errors, the odds go up by 11%. They're 111% of their previous value. If I go from 11 to 12, they go up by 11% of that new value. If I go from 12 to 13, they go up by 11% of that most recent value, over and over and over. So this is a multiplicative change every single time we increase by 1. So for instance, just to drive this home, if I were to introduce 2 spelling errors, it would not go up by 22%. It would go up by e to the 0.01 squared. That's that, or e to the 0.02. This is the kind of key difference. And we'll do a lot of examples to kind of go through this, but it's a percentage change, just like the value of your portfolio. Like if you, for instance, have a 7% return 2 years in a row, that does not mean you have a 14% return. It means something more complicated than that. You have to have a 7% return the first year, and then that is compounded the next year, and you have 7% return on the previous returns. This compound interest is a serious thing, and that's what's the same mechanism is at play here. So like I said, we're going to be doing a lot of examples here with different values of beta, positive values, negative values, betas with categorical dummy variables and all the rest. So if it's still feeling a little shaky, that's totally fine. As we go through code and different examples, you have plenty of chance to practice.